This paragraph is very important for determining the vibratory state of a certain point M of the interference pattern on the observation screen. The important concept of this paragraph is the optical path difference. The optical path difference is denoted by the lowercase delta, which is the difference between the two paths SS2M and SS1M. We can divide each path into two paths, SS2 plus S2M, which is the first optical path, minus SS1 plus S1M, which is the second optical path. And this is the new optical path difference. We can group SS2 and SS1 together, plus S2M minus S1M. If SO is the perpendicular bisector of S1, S2, this difference becomes 0. Therefore, the optical path difference becomes equal to S2M minus S1M if M belongs to the perpendicular bisector of S1, S2. Or in other words, S is equidistant from S1 and S2. If M is the center of a bright fringe, the optical path difference at point M is a multiple of lambda. Lambda is the wavelength of the laser light. K is an integer. If M is the center of a bright fringe, the optical path difference is an integer multiple of lambda. If M is the center of a dark fringe, delta is equal to 2k plus 1 lambda over 2, where k is an integer. Or we say that delta is an odd multiple of half the wavelength. 2k plus 1 is an odd number. This is when M is the center of a dark fringe. K is also the order of the bright fringe. Because to each bright fringe, there corresponds a certain order, which is an integer. Similarly, K is the order of the dark fringe. Because to each dark fringe, there corresponds a certain order, which is an integer. We are going to mention a very important note here. The central fringe is defined by delta equals to 0. The optical path difference at the central fringe is always 0. If we consider the case where S is at the perpendicular bisector of S1, S2, then S2m minus S1m equals to 0. S2m equals to S1m. The optical path difference corresponds to a point where S2m equals to S1m. This point is O, because O is equidistant from S1 and S2. Thus M is confounded with O, and therefore O is the center of the central fringe. This is in the case where S belongs to the perpendicular bisector of S1, S2. Now, what is the nature of the central fringe? Is it a bright fringe or a dark one? The central fringe is always defined for delta equals to 0. So let us replace delta by 0 to find the order and check whether it's bright or dark. If the central fringe is a bright one, then delta equals to 0. This implies that k lambda equals to 0. But lambda is different than 0. This implies that k equals to 0, which is an integer. And this is an accepted value. Therefore, the central fringe is a bright fringe of order 0. If the central fringe is a dark fringe, delta equals to 0 implies 2k plus 1 times lambda over 2, which is equal to 0. But lambda over 2 is different than 0. We obtain that 2k plus 1 is different than 0. This means that k equals to negative half, which is not an integer. Therefore, the central fringe can never be a dark fringe, because there doesn't exist any dark fringe of order negative half. Now let's do a summary. The optical path difference is used to determine whether a fringe is bright or dark. If the optical path difference is a multiple of lambda, we obtain a bright fringe. If the optical path difference is an odd multiple of half the wavelength, we obtain a dark fringe. The central fringe is a bright fringe of order 0. The central fringe is at O only in the case when S belongs to the perpendicular bisector of S1 and S2. Now we're going to determine the analytical expression of the difference S2m minus S1m. We are going to determine the expression of the difference S2m minus S1m as a function of the distance between the observation screen and the plane of the slits, and as a function of the position x of point M on the axis x prime x. Note that D is very large compared to A, since A is in the order of less than 1 millimeters, and D is in the order of meters. As a result, D is much larger than A. Keep in mind that this figure isn't drawn to scale. S1 and S2 are not actually that far from one another, but are extremely close to each other. Now, how to determine S2M minus S1M? We use a certain formula in a triangle. Consider this triangle, for example, MS1, S2. We always have ms2 squared minus ms1 squared equals to 2 times the algebraic value of s2, s1 times the algebraic value of IH. I is the midpoint of S1, S2, and H is the foot of the perpendicular from M to S1, S2. We are going to use this formula and apply it in our figure. We can write ms2 squared minus ms1 squared equals to 2 times the algebraic value s2, s1 times the algebraic value IH. I is the midpoint of S1, S2, and H is the foot of the perpendicular drawn from M to the line S1, S2. Note that IH is equal to OM, so we get 2S2, S1 as an algebraic value multiplied by OM algebraic value, which is equal to, which is actually the abscissa X. So what is the algebraic value of S2, S1? S2, S1 is either positive or negative A. But S2, S1 is in the positive direction, so it is plus A. By factorizing ms2 minus ms1 into ms2 plus ms1, S1 and S2 are very close, and as a result, ms1 and ms2 are also very close, and their difference becomes very small. This difference is to be determined and is very important. The interference pattern is spread out over a few centimeters, above and below O, whereas D is in the order of meters. Then we notice that each of ms1 and ms2 is practically equal to D. ms2 is approximately equal to D plus ms1, which is approximately equal to D as well, and that is 2ax. ms2 minus ms1, we obtain 2ax over 2D. We can simplify to get ms2 minus ms1 equals to ax over D. This relation is to be memorized and is very important. Now we're going to determine the expression of the abscissa of the center of an interference fringe. In the case where S is equidistant from S1 and S2, we obtain that the optical path difference is delta equals to S2M minus S1M, since SS1 equals to SS2. And what is this difference S2M minus S1M equal to? We have shown that S2M minus S1M equals to AX over D. So what is the expression of the abscissa of a certain fringe? For a bright fringe, the optical path difference is a multiple of lambda. Delta equals to k lambda where k belongs to Z. Then AX over D is equal to k lambda. And as a result, X equals to k lambda D over A. This is the abscissa of a bright fringe of order k. In particular, the abscissa of its center. For a dark fringe, delta is equal to an odd multiple of lambda over 2, which is 2k plus 1 multiplied by lambda over 2, where k belongs to z. But delta is equal to ax over d in the case where s is equidistant from s1 and s2. So ax over d is equal to 2k plus 1 lambda over 2. And as a result, we get x equals to 2k plus 1 multiplied by lambda d over 2a. This is the abscissa of the center of a dark fringe of order k. We have determined the expression of the abscissa of the center of a bright fringe and that for the center of a dark fringe of order k.